The focus of this section is going to be on the concept of partial derivatives. So before we get to partial derivatives, let's do a quick review of the significance of derivatives. And we'll start with the graphical representation. So derivatives do represent instantaneous rates of change. However, from a purely mathematical standpoint, when we talk about a derivative, what we're really referring to is the slope of a tangent line. So if this function is y equals f of x, then the slope of this tangent line would be equal to the derivative of f evaluated at a. Now, the issue that we run into once we hit 3 dimensions is that graphs are no longer curves, they are surfaces. So in 3 dimensions, and this becomes a little bit more difficult to draw, so I have brought in a ringer, and my ringer is this racquetball right here. So a racquetball isn't technically a function because it would fail the vertical line test. However, if we were to consider a point on the surface of the racquetball, there are actually lots of different tangent lines that we could get at this one individual point. As such, we could potentially come up with lots and lots of different slopes of a tangent line. So, as such, a single point can have lots of tangent lines, and therefore lots of different slopes of tangent lines. So what we're going to do is, instead of considering all of them, we're going to consider 2 particular ones. We're going to take a look at the xz trace that is associated with a surface, as well as the yz trace that is associated with a surface. So if you'll kindly recall, this is where we set y equal to a constant, and we wind up with a planar curve within the xz plane. We'll just say, for the sake of argument, that it looks like the one that was up top. Whereas in the yz trace, what we're doing is we're going to set x equal to a constant. It'd be great if I could spell constant, of course. And we wind up with some sort of curve in the yz plane. Not necessarily the same as the curve that you see up here. Now, by setting one of those variables equal to a constant, you have restricted your surface to simply, once again, a curve in 2 dimensions. This is the idea behind taking a partial derivative. So, for example, if we say that this here is a after we have set y equal to b, or if this right here is b after we have set x equal to a, then we could figure out the slope of a tangent line in either of these situations. And again, doesn't necessarily have to be the same slope. This is the idea behind a partial derivative. So for a partial derivative, you are going to treat one independent variable as a variable. And we are going to treat all others as a constant. So what we'll do is we'll bring out the formal notation that we use for each of these. So suppose we'll start with the most basic case, the function of 2 variables. We will let z be equal to f of xy. I'm going to flip the page over, and we're going to define what partial derivatives are. So the 2 different derivatives that we have, first one is referred to as the partial derivative of z with respect to x. Now you'll notice that the d's that I'm using for the partial derivative look a little bit different. This is a version of a lowercase delta. This is essentially what you would see as far as the Leibniz notation of a derivative is concerned. The other definition of a partial derivative that you would see is the following. That is the partial derivative of f with respect to x, and we'll treat it as a function xy. This is going to be equal to the limit as h goes to 0 of the difference quotient. X is going to be treated as your variable, y is going to be treated as a constant. So in the difference quotient, we're going to see an f of x plus h minus f of x. However, because y is still a variable here, we will still need to see it as part of the function. So the significance of this is that this would represent the slope of a tangent line in the xz trace. Now that would of course be after you actually plug in a value. Additionally, we can talk about the partial derivative of z with respect to y. Again, your d's are going to look a little funny, and that's okay. For this partial derivative of z with respect to y, or the partial derivative of the function f with respect to y, we are going to be treating y as though it's our variable and treating x as though it's a constant. So when we set up a difference quotient, we're going to see y plus h in the first part. The significance of this partial derivative is that this would be the slope of a tangent line in the yz trace. In both of these situations, it's also as though you are saying treat one of the variables as though it's a constant and take a derivative of the other variable. Now, does this mean we're going to have to go back to the limit definition of derivatives that we learned way back in Calc 1? The answer is absolutely not. We're going to come up with all sorts of derivative shortcuts just like we did back in the day.